for them and more machines and examples for them. And before we do that, which is, let me just show you, this is the part of those not secret project, it's not secret at all, that everything is lenses or dialectica or you name it. So let me just have the lenses definition right here because I'm going to use it very shortly. And also I want to establish my notation so you don't get confused with Brendan's notation, which is great. So we have this category, lenses, say, or dialectica, or C, and the object, so C has to have finite products for that. C has finite products, and then the objects of those of this category are just pairs of objects in C times C. So you have things like A and A prime. You can write them like this, or you can write them upside down. And then the morphisms are the lenses. Basically, the morphisms are from A prime to B prime, are this pair of functions we saw yesterday, but I like thinking about this so that was from Valeria de Paiva's thesis, and when you have this situation and you want to write the pair of functions that describe what a lens is, you always have the get function on top, and then you want the put function, right? So the put function can go from A times B prime to the remaining thing. So here is the put and here is the get, but of course you know that this goes from A to B, and then P goes from A times B prime to A prime. Okay, so that's what this notation is supposed to do. And I like this notation because now I can write composition a bit easier. Well, I think it's a little bit easier to parse. So if I have a composing lenses and you have A prime, B prime, and then C prime, as we said yesterday, and everybody knows the get function is easy because you just compose the top get functions and it's right there. You go from A to C, and then ideally you would like to go from A times C prime. You see, you have to have this line here all the way to A prime. So as Brendan explained yesterday, you just do whatever you think it's reasonable for you to go from A times C prime to A prime. But if you think about this, if you start from A to C prime, you cannot go anywhere because all you got is something going like this and something going like this. So if you really put your best effort to come to A prime, you realize that going from A to C prime, you better make a B arise using this function, then go to C to B prime, and then employ the put function of those two to go to A prime. So it's like a diagrammatic explanation of what I'm going to write here, starting from here to there, using all these maps, this map, and this map to finally arrive at A prime. So if you start from A times C prime, then you really want to make your way to here, and then you first of all need to, unfortunately or not, duplicate this A. So you need to take two copies of this A and go A times C prime. And why did I need to do that? Sorry. Because now I will use this get function to make a B appear. The B wasn't there before, so now I'm going to put the get function here and have A times B times C prime. And you know what? Now it's not that bad. Because from B times C prime I can go to B prime, and then from A times B prime I can go to A prime. Does this make sense? I mean, I know you already know that from yesterday, just another way of thinking about this. So then I will employ this, I didn't give names, that was a bad idea. This is G, and let's call this P, and let's call this Q. So I'm using 1 times Q to go to A times B prime, and then my final put function to go to A prime. So this is the put of the composite function here, of the lens. So this is what we saw yesterday. This is the lens, the category of lenses on a finite product category. And one thing I'm going to use today heavily is that this is a monoidal category. It's also closed, but we're not going to use this today, so I'm not going to say anything about this. So this is category structure with the identity. And now the monoidal structure, can you see here? Not very much, a little bit. I just try to squeeze everything there, so I keep it there and I use it later. So let me just squeeze the monoidal structure, which is not, it's very intuitive, I think. The monoidal structure just says if you have A prime, and you want to tensor it with B prime on objects, that is, right now, the only thing you do is take the product of the view and the product of the state. So that's it. Okay? This is the monoidal product in this category. And even though it uses times, which is a very Cartesian thing to do, just bear in mind that because of the weird morphisms, you see morphisms here are not pairs of morphisms or whatever, they're strange. This is not the Cartesian product in this length category. This is a monoidal product. It doesn't have the universal property of the Cartesian product. So it's not Cartesian or LC. Sorry, my marker side. It's just a sheer monoidal product, and this is going to be used, and it's symmetric because it uses the symmetry of times. Are there any questions so far? Just recapping yesterday's stuff, lenses, or whatever you already knew. Okay, so now we begin with the category of wiring diagrams. So this was maybe 0, the category of lenses, and let me just go to one wiring diagram, well, category of label boxes and wiring diagrams. So now, what we try to do, and by we I mean David in 2013 introduced this, I think it was 2013, and then him with many collaborators spanning over the years, extending this and creating more algebras and more formalism for this, but this was, since then, the idea is exactly the same, the formalism is exactly the same, and the idea is that, the broad idea is that you have some situation like this. These are boxes. Those boxes could be any system you want to think of, or processes of some sort, okay? And then you have some sort of interconnection that actually make those systems behave together, or this talks to this one, and this takes input from this one, and maybe there's a feedback loop here, and all these things. So you have these complex systems in real life, of course, and what this formalism is trying to capture categorically is how, given a specification of this system, and this system, a mathematical specification that is, then this will give you a very nice, thorough description, a uniquely determined description of their composite. So there's always going to be inside boxes and outside boxes, but it's not really that these outside boxes existed before. This is really just the composite system, the composite behavior, the composite process of putting those three systems together and wiring them in any arrangement, in fact, okay, in any reasonable arrangement. So this is what this wiring diagram formalism is trying to capture. This is the broad idea. So let's dive into the specifics of it. So it's a category, okay? It's WC. C label boxes. Well, let me just keep it here. But I'm just going to always have a fixed type here, and you'll see why this is important. So the objects of this category, the objects are pairs of finite sets. Okay, so let me just say x1 and x2, but they're not just finite sets, so both of those things are finite sets that come equipped, they have a little bit of extra structure, equipped with functions, so shear functions, nothing categorical here, tau phi or tau I from xi to ob c. So, what does this thing do? This says, I'm going to have a set of things, and each one of the elements of this set of things, is going to be associated to its type. So here I'm going to have a little x, and then tau of I of x is just an object in C. And this just says the type of this element is going to be blah, that object. Okay? So let me dive into an example before this looks a little bit weird. So now we start talking about those boxes. So these objects are labeled boxes. And x1, I'm thinking of it, and I'm going to change this a little bit, of input ports. So x1 is going to be the input ports of my wire. They're finitely many, okay? Input ports. And not only these are elements of a finite set, but every one of them comes associated with a type of information that can pass through that wire. For example, this can allow, for example, integers. Tau van can allow booleans or something, okay? And then this just says what information I can allow this wire to carry around. Now I have the output, so this is x1, and I have the output ports, the same exact story, different, doesn't matter how many they are, and then also they come together with some types. So tau of b1 can be, doesn't matter. reals. And what I've drawn here is exactly a set label box, because every port is coming together with its type, which is a set in this specific example. Set label box. Okay? So here we have this pair of elements with ports inside. The elements of those sets are ports, and each one of them comes with a type. Now let's see the morphisms, which are the interesting part. I mean, this is also interesting, but let's see what the morphisms are. So morphisms that go from x1, x2 to another box, y1 and y2 are, I'm going to define them, but before I define them, I want to make sure everybody understands where this definition comes from. It's a very intuitive one. Okay, so x1, x2 is a label box. There it is. So input ports here, output ports here. Now, maybe contrary to other wiring, like string diagrammatic notation, so most of you and many category theorists and people that have worked with the string diagrams and stuff always expect these guys to be morphisms and these wires to be objects. This is a totally different viewpoint, well not totally, but it's a different viewpoint that says my boxes are going to be the objects, and this picture, this random wiring picture, will be the morphism, okay? So it's a different way of perceiving situations like this, and you'll see how morphisms depict this difference between viewing morphisms as wiring arrangements. So now, I will have a box in here, and I'm not going to draw another box with input ports and outputs next to it. Instead, I'm going to draw it outside it. So this really wants to capture the inside, the zoom in, zoom out situation when you have a complex system and you want to actually decompose it in the smaller pieces it comes from. So this is my x1, x2. So this is x1. As I said, I mean, this is x2, and here I have y1, and here I have y2. Okay, so this is my pictorial representation of what I am about to write here. And the morphisms in this category tell you what you can do with your wires, what possibilities you have, what is your freedom here. So, it's going to be a pair of functions. Our functions, I'll say something about the types in a second, okay? But first of all, it says, I have the set of outputs y2, okay? I have this side of the box. This is where the inside box talks to the outside world in a sense. And this function tells me what kind of connections I can make this wire to talk to each other. So where can the information come from? And the first function tells me it can only come from output ports of the inside box. Okay? So this is the pictorial representation here, and this says, and this is like, it is a function, this means every output port needs to be mapped to where the information comes from x2. Okay? So this is one inside box. And here I like this. So here in my function, I am going to add this joint addition of sets that is in here. listen.
Like a fish.
Like a fish. Where's my wiring diagrams is what we're talking about.
What are you talking about again?
We are talking about wiring diagrams and label boxes, whatever they are. Is it better?
Yeah, fine.
Fine?
Yeah.
Okay, let me just if there are any questions we can discuss, because this is the basic category that we're kind of working on. So they are functions that do this. They tell you where the info comes from. So info where info comes from. But of course, I said something about wires and types. And what does the type have to do with anything? Well, only attached to wires if they have the same type of information. If the one wire has booleans and the other has real numbers, how on earth are you allowing the interconnection between them? So such that the types are respected. Types are respected. So this means mathematically it's not such a big deal. All those things have types. These have a type. This has a disjoint union of types. And then this maps down to C. Well, this needs to commute. Okay? So every time you wire a thing with another thing, they have to have the same type of information allowing to go through it. Is this clear so far? Any? What's up?
Pretend I'm not here.
Okay, Yele is not there. I don't know who this person is. Okay, let me now try and formalize this a little bit. And beautiful functor that connects this category with that category. Before I do that, I need an eraser, which is here. Thank you. Oh, this is slippery. Okay, so the idea here is that we learn so much pieces of knowledge that do not connect to one another, but we want to view the big picture of what we're doing. Yesterday, we saw things about optics. So let us now see this category as an optic. Many of you already know that or see that already, but let me just say remark. So there's an underlying category which I didn't specify, but it's not so hard to see. There is a category I've been using here, TFS sub C, which are the typed finite, so C-typed finite sets. Oh. Okay, so what is so nice about them? Well, the objects are exactly what we've been talking about. So they are actually just sets with typing function. Function is that tau. Every element, some object of some type in category C, and the morphisms are just x to y functions that commute, as I said, with the types. So if you want to think about this a bit more, this is fin sets, kind of, well, slice with objects in C. I say kind of because this is a slice category, but objects in C is not necessarily finite, so this is not really true. But if you want to think about this as an arrow category, you have both those things happening into sets. So you can form the arrow category. In any case, this is just an abstraction of what type finite sets are. And this WC now, you can see by looking at this situation here, looks very much like a prism. You have a function between the outputs, and you have a function going to the sum of those two things. So in fact, what I did here, WC, is prism of typed finite sets in C. So this is the one observation I wanted to make sure everybody follows. This category is the category of colenses, of the dual thing of lenses inside this typed finite category that we're using here. Okay? One thing I didn't say, and I should have said, maybe it's too late, this is a symmetric monoidal category. It's not too late, of course. Symmetric monoidal category. And if you want to think about this, you're just taking two labeled boxes and you position the one below the other, and this is parallel composition basically. So what you do is you take the disjoint union of the typed finite sets on the inside and the outside, and that gives you a beautiful new wiring, label box here with x1 plus y1 as inputs and x2 plus y2 as outputs. Okay? This is metric. It's metric because it doesn't matter which comes on top or below. It's isomorphic and everything is fine. So now what we want to do, slowly but steadily, we want to build algebras on this category. Algebras on this category means lax monoidal functors with this domain landing on cat or on set or your favorite easy category when you want to give semantics to those empty boxes. Remember, these boxes are empty. The only thing that we've been talking about all this time is ports and connections, but we don't say what goes inside. We don't say something about the essence of this. This is an interface. This is syntax in a sense. So now we want to start thinking about positioning systems inside those boxes. But before we position systems inside these boxes, we realize that it's much easier if we want to view this whole box not as having an input set of ports, output set of ports, everything has a type, but you want to view this somehow internally in a category. You want to view this internally in C. So what I'm going to do now is I'm going to build a functor from this category to the lenses, and then we're going to build the algebra. So the real fun happens on the lenses, but first we need to make sure that every one of these very nice formalism actually corresponds to a lens in a well-motivated way. So now we're going to build the functor to lenses. So to functor to LC. Any questions? Okay. So there is a functor to LC, and let's see how this is induced. Before, in the previous age, before prisms and optics and all this, with David, we had this functor in some paper, and it's just a very nice functor. You can write it down. But now, viewing this category as a prism and viewing the other category as lenses and knowing that both of those are optics categories, there is actually a much nicer way of expressing this functor that is induced between two categories of optics. And that's the thing that we realized yesterday and we talked about in the night a little bit. So this is connected. So I'm going to build this functor to L of C, but this functor really comes between the prism and L of C here. There is a functor, so it is induced, it will be induced by, well, I'm going to write a strong monoidal functor, and I'm going to explain strong monoidal functor, which I'm going to call hat. Okay, that goes from typed finite sets, this category here that underlies all these things going on here, op, it's a contravariant functor, to C. Okay, so this functor here, we're going to build it, and then this is going to induce a functor between the prism and the lenses because they're both optics in a nice way. So what does this functor do? This takes any typed finite set here. So it's x and tau. Remember this tau that says I have a finite set and I assign an object in C as a type of every element in my finite set. And this maps it in the C world to the product of all the types. So if I have a finite set, I can take the product because, of course, C has products. Okay? So C has products, so I can take the product of all the types. Remember, all these types are in C because of these typing functions for all x in X. So this is a very well-defined object in C, okay? So what does this do? If you're looking at this as an input port, it says, forget about saying, oh, I have the first port, the second port, the third port, and then I have integers, reals, and booleans. This actually takes right away the product of integers by booleans by reals, okay? That's the only thing it does. It goes away from finite sets to inside the C world. That's what's going on here. And this functor is a contravariant functor. I may want to elaborate on this, but maybe you see that already. Bless you. So if you have a function, again, if you have a function here, okay, if you have a function, this is a typed function that commutes with the types, then, of course, I can form the product of the y elements in y and y. This is just great. But now, this is a contravariant functor. This produces a map the other way around, okay? Why? I'm glad you asked this question. So let us go somewhere else here. I have a minimal example here that will help us. So suppose I have a wiring diagram like this. And I am allowed to do this this just says this input port comes from this one, this goes nowhere, nobody cares about it. So A1, A2, and B1. So what does the function do? The function says I'm going to go from Y2 to X2, and I'm going to map B, well, just B, there's no other, to A1 and B that. So this is a typed finite set situation. But now what I want to do is take products of those types, okay? So I'm going to take the product of B.
Oh, then you project.
You project. And then you have tau of A1 cross tau of A2. Of course, because I map them together, they have the same type. This and this is the same. So now you just project on the respective thing. So taking products really flips your situation around. Before, yep?
The other way around. Yeah. The projection goes the other way.
Oh, yes. You're right, you're right, you're right.
According to what you said.
According to what I'm saying, it's just that I flipped them. I shouldn't, actually. Let me just, yes, you're absolutely right. Thank you. So this is tau of B, and this is tau of A1 cross tau of A2. If I apply the product factor to those things, and now my arrow goes in the other direction, and I have P1, okay? Because is the same. Tau of A1 is the same of tau of B because they are wired, and that's the only way things can be wired together if they have the same type. Everybody satisfied with the contravariance of this functor? More or less? Okay. Yele?
No.
Just avoiding. Okay, and the other note here is that this is a strong monoidal functor. So the says the strong monoidal part, interesting, is it turns, pluses. So this just says if you have a disjoint union of sets and you decide to take the product of their types, then this is just the product of the types of the one times the product of the types of the other. So actually, let me just write this down. So if I want to take the product of types existing in some disjoint union, that this is isomorphically the same as taking separately the one and the other times. So this is x in x, and this is x in y. So this functor here, if you're not a fan of abstractions, then this is fine. But the only thing I want to say is that this is a very well-defined functor induced by taking product functor. This is take products. This is the gist of this. Take products. Okay? So now what's going on, and it's related to what we talked about yesterday, is that I want a functor from prism of T of S sub S to L of S. And this is lenses. But yesterday we realized that this prism is only the lenses in the opposite category. And since this is the lenses in the opposite category, and I just built up between the underlying categories, then L, the lens construction, is functorial in their inputs. And in fact, this induces a functor L of the product between those. So this functor, which has been there for ages, and David has been using it, I have been using it, people have been using it, is really just an optics functor. Okay, so that's a very nice realization. Optics functor, well, a lens functor basically induced between things. And just like in optics, because prism is a different type of optic. Okay, so that was the functor to the lenses, and that is part of the whole everything is lenses or everything is dialectica situation. Okay? I keep saying dialectica because lenses are also dialectica categories that were built for linear logic purposes. The topic of today's talk. So there is the functor, and now it's about time we go to the algebras. Our is still empty. The only thing that happened with this functor is when I viewed this thing before, so I had this inside-outside situation, and I was viewing them as finite sets. Now I don't view them as finite sets anymore. I view the input and output as one object in C, one object in C, one object in C, and one object in C. So now I take all the types, I smash them into one object, which is a product of types in C, and the only thing I'm saying is, you know what? This functor, which is contravariant, is going to land in L of C. So now everything is going to be flipped, you see? All the things are going to be flipped. The times comes from the plus because it's a contravariant and strong monoidal functor. So that is exactly how this lands on here. So let me just say that this functor, so let me just write this functor down to make it a bit easier. So WC, which is the prism, going to L of C. What does it do? It takes x1 and x2 and it maps it. So now I'm going to make a weird flip here, and I'm going to start viewing inputs and outputs the other way around, which is maybe similar to what Brendan was doing, but maybe not. So this is going to be the product of types, and this is going to also be the product of types, but this is going to be of the input, and this is going to be of the output. OK, so now this is going to be my A, and this is going to be my A prime. OK, so my A prime is the input. My A is going to be the output. My B prime is going to be the input. My B is going to be the output. Those two functions I have over there, the length thing, remember, A prime, B prime, consists of two functions. One function going from A to B. So this again gives you now the flow of information. The real flow of information now goes in this direction. And this other map from A times B prime to A prime says, if you want, you can start from A, then take products of things in B prime, and then feed it into A prime. The picture is the same, but it's a little bit abstracted from what I had before with input pot and outputs.
Outside, inside, and you go inside, outside.
Yes, so the flow is different, exactly. Well, kind of. The flow of information is always the same, but before I was thinking of where does this come from, but now I'm saying, OK, now this is going to go this way. Exactly. This is the different view between profunctor optics we were talking about yesterday and lenses, I mean, diagrams. Because here I have the input going onto the output in a very clear way. So you have A prime in the middle and BB prime on the outside. But yesterday, the profunctor optics were a bit outside in. Okay, there were things between A and A prime trying to go, B and B prime trying to go to A and A prime. We talked about last night a little. Okay, so now an algebra, a Moore machines algebra on this. Said these boxes are still empty. There's nothing in them. We're still talking only about the possible syntax for those boxes, the possible interconnection of those boxes. And actually, let me just make a very quick example. If I write here, can you see? Just why is everyone very silent? Everyone's good? What? Gaps? Oh. What? OK. So that's.
So Moore machines is the ones with state, right?
Yes, the state machine. Yeah, the ones with state. Mealy machines also have state, but then the output depends on both the state and the input, not just the state. So Moore machines only depend on the state for what they output to the outside world, but Mealy also on the inputs. OK. Very good. So let me just try and elaborate on what we have done so far. It may seem a bit like overwhelming, but it's examples. So suppose I have this interconnection of boxes. I said earlier, whenever you have any reasonable interconnection of boxes, you can express it during diagram formalism, and now using the lens. So let's understand how into a pair of functions that exactly what we've been talking so far. So just give names to those things. So x, y. So these are the types of the inputs and the outputs now. This is already in the product world. This is w, z, and e. So this is the type of information sitting on the wire, and I better find a way to express this as a lens. That's what I'm going to do now. So the first point here is a little bit. Remember that this category can only talk about inside-outside boxes, okay, and also parallel boxes, because this is the monoidal product. It doesn't have any primitive. It doesn't have any, for example, composing in parallel, serial composition. This is not part of the category structure. This is external in a way. This is something you need to build. So let me show you how using all these two, only those two things, this is the Morphisms and this is the to actually talk about this as a lens, okay? So let me just put this first. So this is the funny part. This funny part says, I have no way of understanding what this is doing on the right-hand side of this, so I better bring them in a series, in a line, because this is the product, okay? But now I better make sure that none of my wires break. They need to do exactly what they were doing earlier. So these two inputs are going to stay as they were. So there is a Y here, there is an X here, but now I brought this on top. You can put it below, you can put it in the middle, it doesn't matter. So you put this on top, okay, so this is it, and you make sure that those two output wires actually feed in that box that you just moved. This is really just moving the box on top and preserving the wires. It's like a game. So now you have this situation here where this wire is still W. You see this is that wire, and this wire is Z. And of course, they go inside. And now you have an E coming on the outside. So this is just a rearranging I did for personal purposes to understand this wiring diagram better. Okay, and now I am going to write the length that expresses this. Of course, this is the same as that. And what is the length? Where the length is the easiest thing in the world. As we saw earlier, everything ends up being somehow projections. So let me write the put and the get. But before I write the put and the get, remember that this is now my input of the outside world. This is the output of the outside world. And I need to be careful about the inputs of the inside box and the outputs of the outside box. Okay? So first of all, the get part goes from the outside of the inside box to the outside of the outside box. So this is going to go E times W times Z, because this is the outside of inner box. Okay? And I need to just say, I need to denote a way that this goes to E. But this is just the projection on E. This just says, you know what? There are three things coming out of this monoidal product. Well, I don't care about those two things. They do something else. The outside world only see the wire with these on it. Okay? And now I need to write down that says, given something coming on the outside of this and the inside of this, going inside to these little things here. Remember, I switched my view. Okay? So these guys here is going to have the product of the things I want to actually under the wires. So let me write this down. So this says E times W times Z. So this is the outside of this box, okay? And now I'm going to take the product of this with the two inputting wires, X and Y. And then I need to give a way of feeding information on this inside box. But I see what the wires do here. All the wires are used, all of them except the E. The E is the only thing going to the outside world. All of these wires are fed back inside this box. So what I have here is just the relative projection to everything except E. W, Z, X, and Y, and it's another some sort of projection. So every time you have this situation, these wires are really given by projections, signifying where the information comes and goes to. Is this clear, more or less? Okay, do you have a comment, David? No? Okay, so this is the length. So let me make it maybe right. So this is an A prime. So this is an A prime, and this is an A. So let me just write the B prime and the B, okay, in the length notation. So this is the B, okay? So this is the A prime. This is again the A prime, and the XY is the B. And this all goes to, sorry, I made a mistake, a rookie mistake. All the, no, sorry. Everything is under control. And now this is the inside of that box right here, which is A. So this length completely determines the wiring interconnection of that thing inside there. So still going through all these empty boxes situation, and now we're going to put more machines inside them. So number 2, 3 is more machines as algebras. What algebras are? They are lax, monoidal functors into cut or set. Let's say into cut, which is a little bit more. Okay, first of all, kind of understand intuitively why do we keep saying that putting things inside, putting system inside, and allow them to interconnect in random ways will give me a symmetric Laxmonoidal functor. Okay, symmetric. Okay, think about that. We're going to stick to the lenses category now. So we've already done this first part over there, which is an optics functor, and this goes to cat. Okay? What are the elements in here? It's a pair of elements in C, which we keep seeing as boxes. Okay, this inside and outside box. Now, what does a Laxmonoidal functor do for us? First of all, functor. So it better map this empty box, complete box, to a category of things. So how are we supposed to think about this? Is that now I'm going to give a category of possible inhabitants. Category of inhabitants in that box. I cannot write this. Okay, can go in here. A person can, a machine can go in here. A continuous dynamical system, abstract machines can go in there. Various algebras can go in there as long as they form a category. And this actually gives you the meaning, the semantics of those empty boxes. It tells you what can go inside. And every time we want to model a specific system, this mapping is going to change. It's going to give you a different category of things you can put in there. But then I would like to for a second what this does to morphisms. Okay? So remember what morphisms are. Sorry, is there a question? No? So let's remember what morphisms are here. They are bigger boxes sitting on the outside, and this morphism is based to the outside box world. Something like this. Okay? So this thing, suppose, look at what this gives me. There is another category of things that live on the outside box. Okay? And this functoriality, this just actually not reality. This mapping of the functor on the morphisms gives you uniquely determined ways, given all the inhabitants of the inside, construct something on the outside box. And that's what we mean. We model systems by algebras. Given this map is the source inhabitant. So if these are Moore machines, the big thing is going to be a Moore machines. If these are differential equations, the big thing is going to be differential equations, uniquely determines the composite inhabitant.
Why I missed this?
So this functor is a mapping between objects, which are the systems, to objects of the outside. This functor gives all. Then this is also going to be a Moore machine. And this gives you the way, given this Moore machine, to construct the outside Moore machine. F is a functor, meaning every Moore machine. The description is going to be the same.
Why? Could I map the first box to like group and the second box to...
So then you
Sounds.
Is it going to be better? What? Yep. What's up?
I'm sorry, I mean, this is going to be really silly, but how do you distinguish, you draw these diagrams with three boxes there,
Mm-hmm.
but technically there is, am I correct in understanding that there is no way to distinguish that diagram from a diagram with a single box with all the product of the inputs and outputs?
This mean you mean?
Yeah, I mean, however you do it, because you can't really distinguish between.
Operad or the Monoidal category?
Yeah,
At
that's
least the Monoidal category, but if we use the Operad, we can.
Yeah, this is my, so, I mean, right now, this was defined as the one of the categories, there is really no way to.
I don't understand. There is no way. I understand this intermediate. You start from one solution.
Sure, but you put three boxes, so it's.
I mean, this is A1, A2, and A3. These are specific. Okay, and then what I did is I put A3 on top. You could put it very similar up to isomorphic expression.
Yeah, but you wouldn't know anymore that in fact, you don't if you write it just by using the internal product of the category. You don't know that it had three holes. You have no way of remembering that it had three holes. The moment you take a product,
Yes.
You don't know that it was two holes.
Yes, that's true.
Hole with
yes.
With all the wires.
Yes, and why is that bad?
Well, because you can now place, maybe you're wiring I mean, I don't know it's bad, I'm just asking.
Ah.
So that maybe not go into trouble by placing a big box which gets things around. Now, I know you have loops, so that's not. Plugging the output wires in, and then I'm placing a large box.
Yes, you're moving. There's a map from the tensor of three things.
It's just.
But lying operand.
Yeah.
Is that what you're asking?
Yeah, but
one allows you to have.
You're saying you can plug in a thing into this big box that doesn't decompose into.
yes, that's what I'm saying. Exactly. I'm saying you can plug in things which don't decompose into products, so actually the operatic picture is not the same as the monoidal picture. It's not.
Every monoidal category gives you this operand. Yeah. This operand is the underlying operand.
Not in the monoidal category.
No, we work in. The algebras for the operand and the monoidal.
You're worried about the Laxmanoidality of the functor, the fact that it's not strong monoidal. So given an element in this thing and an element in this thing, you can get an element in their monoidal product, but not vice versa.
Okay, I am going to.
We can talk about this.
I will delegate my understanding to Jules because he clearly understands what my problem is. He's convinced that I'm worried about Laxmanoidality.
Okay, so there is a nice, maybe that helps you. Maybe that will help. If you have a monoidal category and you take its underlying operand, you can always do that. You have a monoidal category, you take its underlying operand. Okay? Then the algebras on the category and the algebras on the operand are isomorphic. There is categorically, this is a fully faithful functor. There is an isomorphism between Laxmanoidal functors on the boxes and on the monoidal category operand functors on the operand. This was in Tom Leinster's book. maybe that's, we have.
Get to talking about the Laxmana F.
Mm-hmm.
There's been things that fill in the product of boxes might not come from things that from the. I think when you get to the Laxmana
Monoidality. Of this specific F or the Moore machine F? It doesn't matter.
Okay. But if you didn't have the feedback loops, this wouldn't work.
Yes, yes. This,
So that is
yes.
necessary for this to
Absolutely.
Okay.
Yes. Otherwise, you wouldn't be able to move the same, because then you wouldn't be able to produce. Yes.
Yeah, because then it would still work for 3 separate boxes as an operand, but it wouldn't work if I plugged in a single box with a large type, because it could do wiring in that way.
Mm-hmm,
I see.
mm-hmm, 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 mm-hmm. Okay. So, machines, those boxes. And then we're going to see how this is and how this is a monoidal functor. What is the, do I need, I can go on.
The time is 20 minutes past 11.
All righty.
19. We are in Germany. You have to
Maybe I'll write the Moore machine, and maybe, David, you can write the Fibonacci right away, because my other example takes long. Is your example a bit? I think you should do it, because mine has, I think mine is a bit harder. If you don't, yeah, whatever. If you think that I do the other. Okay, so the rough diagram operand for the monoidal category. For example, e.g., let's choose C, our typing category, to be set. Okay, so now all my wires carry. Okay, what I'm going to do is define a functor machine. Is category basically. So now there's category projects. Okay. In C, which is an empty. I keep the category. So M of A prime has objects. So let me objects of M A prime are Moore machines. Namely, so there are two ways. Well, there is one. Realize with David that the definition is great. You can write down every Moore machine, every finite state machine of this form has a set of states. So for a set of states X, for example, the Moore machine with that set of states and input and output A and A prime is a length from XX to A prime. So this is a Moore machine. Let's decompose this and understand where this comes from. This is given by a pair of functions. It goes from X to A to the top, okay? And this function, so this is given a state, then the world always sees an output depending on the state. And then we have this situation here that goes from X times A prime to X. So this is, what does this update function do? Then this takes an element of the state, the current state, and then something that comes from the outside world, and then it produces a new element of the state. So every time, at every clock tick, I will give an example right now just to make this clearer. There are things coming in, changing the state, and producing an output that the world can see. And that happens over and over again, okay? So this is a Moore machine, all right? And as I said, this is a category. Do you want to say what the category structure is? Okay, is this clear, first of all, this definition of a Moore machine? Outputs coming from a state and update depending on a state and a thing. So let me actually give an example right away. Let us give the following example. Sometimes Moore machines are shown like this. So S0, T1. So what is those two blobs? This is the set of states. So X, the set of states, in this specific example, is just S and T, just two states inside my Moore machine. Those two things that come below the states are the output that the machine spits out when it sees S and T. Okay? So now we have the output, which is A, is 0, 1. Okay? Because 0 and 1 can come out. And I already have the output function. X output function to A just takes S to 0, because that's what this little blob here means. And it takes T to 1. Okay? Given the set of states, that's the input set. This is the output function. And now I'm going to give the output set, but the input set is the same in this specific example, is 0, 1. And what I'm going to do now is saying, whenever this state receives a 1, stays where it is. But wherever this state receives a 0, goes to the other state T. Now for T, wherever this state receives a 1, goes back to S. And whenever it receives a 0, it stays at the same state. So this is a very common Moore machine or finite state machine depiction of what's going on. But if I want to write this in this way, in a lens way, if I want to write this in a lens-specific way, I have the output function right here. And now I want the update function. So the update function takes the set of states, so X, and then the set of inputs, which is again 0, 1, and goes to a new state. So this says, for example, I'm not going to write all of them, but if I have S and you feed me 0, who knows what I'm going to do? Well, this shows me what it does. It goes to T. Whenever you have an S and somebody feeds you a 0, then you change state and you go to T. And you can write this for all combinations of S, T, 0, and 1. Okay? So this function here is the update function of this Moore machine. This is the depiction in this language, and this is a depiction as a lens, which gives you the algebra on the operand, on the monoidal category. Okay? So this is an example of a Moore machine. You can do anything you want with these two functions. It goes without saying. And what I want to do next is show you the functoriality. So that's what I tried to really show before. For any wiring arrangement here, this will give you, I will give you one way, a nice way in my opinion, of producing another Moore machine with this input and that output here. Okay? So let's see that part. So mapping on, mapping. Very good question. I'm trying to avoid it, but it's not such a big deal. No, this is great. This is great. If you have a, so notice that this category has fixed input and output, A and A prime. So you can now have a different Y, so a different set of states, but on the same input and output. So that's an excellent question. So then you have another thing like this. This is another Moore machine. A function, a morphism between them is a function between the underlying set of states that commute with the output and the update. Okay, so it's again slicey. It's slicey because you keep A and A prime fixed for this specific category. Jules liked that. Jules.
I was wondering how you get a category just objects are lenses, because lenses are usually morphisms to the category.
Right, but now if you fix input and output, then you get it. Yes. And then you can take the Grothendieck construction and have a category of all lenses, all input, and then boom. And it's a monoidal Grothendieck construction. Okay, I stop then. Okay, the mapping, other questions? The mapping of the Moore machine functor on morphisms, which are wiring diagrams. Okay? So now let's understand what's going on here. I have an inside box, I have an outside box, and I have some wiring arrangements, which we know very well is given by a lens, which is somewhere here. It's given by a lens. So what I need to do is apply M to this pair of functions going from the inside box to the outside box and define a new Moore machine. Okay? So M on. I get that goes from, let me get my terminology right, from A to B, and I put that goes to A times B prime to A prime, because this is a morphism in my lens category here. Okay? So now this is an awesome functor. This functor takes a Moore machine with input A and A prime and produces a Moore machine with input B and B prime. How? By post-composing with a lens. Everything is a lens. Again, the slogan comes handy. Post-composing with lens. And this is a very nice description. This is not the description that, it's the same thing, but it's not the way that this was introduced. That goes from XX to AA prime. This is my Moore machine, right? This is the initial Moore machine on the inside box. And then given a lens, which gets you to the outside box, the only thing you need to do is actually lens compose those two lenses. So the fact that we can view Moore machines as lenses themselves make this algebra a piece of cake. It's just post-composing with the lens that expressing going from the inside to the outside lens, which is the same as a wiring diagram. So I will write this explicitly, but the idea is exactly this. So let me erase this. So do we need this?
Can I ask a question?
Anything.
So, you view your wiring diagrams as lenses.
Mm-hmm.
That's fine.
Mm-hmm.
However, now in this picture down there, this cumulative diagram, yes.
Mm-hmm.
There you say, well, the functor is from lenses to cat.
Mm-hmm.
However, you view the lenses now as wiring diagrams in the picture, right?
Okay, so that's part of the functor I described earlier. So you take a box. It has input-output ports. You stop thinking about this box as having input-output ports and types, and instead you view this box as having one element of C associated on one side and one element of C associated on the other side. What are those elements? The products of all the types.
So she's pre-composing with that thing there.
I'm always doing this. Yes, I'm always doing this. So you see, instead of having here I may have, for example, this could be Z times R times bool. This could be R times, I don't know, natural numbers.
You're saying in that picture, you pre-compose with this embedding.
Yes.
Yeah, like you're drawing the picture, but you're secretly using that thing.
I choose to view the picture like this now.
Because
It always comes from a box like this, but you don't, it's fine if you think of it straight like this.
No, because lenses are more general than wiring diagrams, right? The functor is not.
This functor that takes products, yeah, this is not an isomorphism by any chance.
So yeah.
Mm-hmm.
Okay. So if you really start from lenses there, you could pick something bigger.
Yeah.
But in our algebras, we don't.
Yeah, so what we are saying is that the mapping you're really defining is from all the boxes
That
which
map
are
into that.
pre-imaged to that functor.
Yes. But this functor is defined agnostically to that. If you look at the definition, then you don't see the products.
Works on all lenses, but
Yes.
you care more about.
Exactly,
the
yeah.
lens than the
Yes.
image.
Definitely,
Yeah.
definitely.
Right.
Absolutely, yeah. This functor is by no chance an isomorphism here. Yeah. Mm-hmm. True. Can I erase this? One is looking mysteriously. Okay. So now the last thing I want to do, you are tired, is write down exactly how given a Moore machine on the inside, it gives you a Moore machine on the outside, just like write down this composition, which I've written over there. And then I'll make an example, or David will make an example, or somebody will make an example with specific Moore machines, like the one I showed you there. Would be one composite of a composition of Moore machines. Yep.
I have a question. Like Moore machines seem to be a particularly happy
Lens.
example because they are basically lenses.
Mm-hmm.
Like their inner structure is actually very
How
much
cool is
compatible
that?
with
Yeah.
your wiring structure.
Yeah,
And
that's
the
not
question
true
is-
in all the algebras.
The question is how good it is to wire things this way when the thing you map the lens to doesn't look at all like a lens. like when you really have some ugly stuff,
Ugly stuff.
like not lenses stuff, like shit stuff.
So there's generalizations of lenses, like continuous dynamical systems look very similar to this. But if it's completely different, then maybe lens is not a good category as your...
Well, maybe what other classes of automata you can think of in the same way?
Petri nets.
Petri nets.
Medium machines.
If you have any Laxmana functor from lens to set or lens to cap, then that means, or prism say, then that means you'll be able to draw these wiring diagrams and make sense of them. If you can't come up with any beyond more machines, then
So you are still like
then that's okay.
you can be like selecting.
That's like, yeah.
But then you basically have to select algebras which are somehow compatible, which have some lens structure.
I don't
I mean, there's a
think.
functor from lens to cospan, for example. So any hypergraph category gives you a.
Yes.
Yes. There's lots of things.
Okay, no, that's useful. This is what I was trying to understand.
Okay. Also, this functor is representable, right?
Yes.
So it's particularly nice, but it can also have
Non-representable functors.
things.
Yes, I mean, it is a particularly happy example, but it wasn't on purpose per se. I mean, it happened to be a very nice example, but Moore machines are also nice. There are other examples. I don't think this.
Any tracing nodal category
will give you one of those. Even the abstract machines, I don't think they are lenses. I tried one day to see whether they are lenses themselves, but so maybe they are, maybe yes. So I have examples for sure that are not of this particularly nice form. Sorry?
So doing this something like open Petri nets with like input and output types.
I've never done this for Petri nets. David, have you done this for Petri nets?
Given a wiring diagram, you get a Petri net.
No, but he meant putting Petri nets in the boxes, I think.
Putting a Petri net in the box.
Or a flavor of Petri nets where you have input types and output types like
That would be nice. That would be awesome.
string transducers.
Because that would be another way of gluing Petri nets using the wiring diagrams. I don't know.
String transducers.
I've never thought about this. Yes, exactly. These are definitely. Okay, so let me just write this and the monoidal structure, and this is done. The Moore machine algebra is done. And so here I have a little lens looking on the outside by A prime. So this is A prime, this is A, and this is A prime. And here I have B and B prime. And I have this usual situation of being able to loop and go on the outside. So what I'm going to do is just write down the composite of those things. So how can, given this inside Moore machine, view this as understand the composite Moore machine or the Moore machine that lives on the outside, giving any wiring diagram interconnection here, is the following. So the output, of course, will go from X to A, first of all, the output that I started from right here. And then we know very well that the lens gets to go to the outside world. So that's going to be the new output function of the Moore machine. And then to take X times B prime to X. So now I want X is the set of states. So the set of states is the same, by the way. Set of states is the same. Again, this is not necessarily always this is the functor we define right now. So we want to take a state and then an input for the very outside world and update the state on the inside box. And how do we do that? Well, this is shear lens composition down there. So I'm first going to duplicate my state to view my state twice. Oops. View my state twice. And then I will first output something for the state. So I have 1, and then output, and then 1. And I have X times A times B prime. Well, that's just great. When you have A and B prime, you can take the put and have X times A prime. And this is the update of your dynamical system, of your Moore machine, and back to X. So given an input from the outside box right here and an inner state here, do this lens composition, which is indeed a very happy composition, and this will give you an updated state on the inside. And that is how, given a Moore machine and any wiring diagram in the connection here, any of the crazy things I just erased, we're always guaranteed to have a Moore machine specified completely by those two maps that lives through the B prime and B to the outside world via this. Okay, and let me just write the monoidality. Monoidality, so Lax monoidal structure. Okay, so what is a Lax monoidal structure? Well, it says, if you take, because this is the Cartesian product, this is the product in cat, two boxes here, well, the Moore machine is living inside those boxes here, you better give me, so this is just like having something in here, a Moore machine and something in here, and now I want to produce a Moore machine living on that box, which is the monoidal product of those two things. So I better find a way to go to M, A times B, and then A times A prime times B prime. Okay, so remember, this is A, and this is A, this is B. So this whole thing is A times B, and this whole thing is A prime times B prime. Okay, so I want something that inhabits the outside box per se, and what do I do? Well, this is a Moore machine, right? If this is a Moore machine, then this is just a lens from XX to AA prime. Okay, so whenever I have one thing like this and then a different Moore machine on the other thing, YY to B prime, then I want something that lives on this, and that's not so bad to do because you have a function here, remember the lens here, and you have a function like this. You also have a function here and a function like this. So for the output, for example, you can have X times Y and X times Y, and here have A times B and A prime times B prime, because this is how this looks in. And here I'm just going to take, for example, F and G here, and I'm just going to do F times G, and then I can do the two update functions here. So update times update the other up to some isomorphism and get a map here. This is the Lax monoidal structure that says, given a Moore here and a Moore machine here, I'll always go on this parallel composition. Okay? So this is the Lax monoidal structure of the functor that allows you to inhabit pictures like the one I just erased, and it was, you have to first bring them all into parallel and then do stuff on it. So far, so good? Okay, so this is the structure. And now I was thinking of doing another example and then compose it with the previous example, unless David wants to do the Fibonacci. No? Okay. All right, so let me keep that there. And I'm going to definitely use this composition here in a little bit. Do you want to take a, are you tired? Should I keep going? Okay. There's no luck. What?
If you want me to give the Fibonacci example, I can. Whatever you want, or not at all. If you think it's nicely going after these things and it's going to elaborate on how a Moore machine gives you something interesting. Maybe.
I'm curious too.
You?
Okay. Yeah. Curious.
You're curious for the Fibonacci specifically?
Okay, I can do it.
Sure.
Yeah.
Okay. I will help here. And I can also do my example after if people want. It's not.
Oh, do I need to wire reference?
I don't know. Maybe not. What?
I didn't prepare.
It's
Okay. Given any function, we can make a Moore machine out of it. So if you have a function from A to B, we could turn this into a Moore machine with, so how do we denote Moore machines? Like B as the state, and then A times B, the update is throw away B, and then use F. And then the readout is just B. So this is terrible notation. Update is given by, I'm going to throw away the B.
Are you writing it as a lens? Or
How should I write it?
can you write it as a lens?
This is
Yeah.
the pair of functions on the right is the length.
Yes, the type and the function itself, right?
B
So this is a
the
map
set of
from
states.
B,
B,
B
very good.
to AB. Why is it a map like that? That doesn't make any sense. Oh, to BA. Yeah. Okay, so let's try to. So here we're going to put. Okay, right. So for these lenses, we put the output on the top and the input on the bottom. Okay, getting there. So this F is then recorded as a thing that outputs the current state, takes the current input and the current state, takes the current input, current state, current input, throws away the current state, and just uses F to, okay. Okay, does that make sense?
So the output function is F, right?
If I run this machine given some input A, what'll happen is it'll start out, sorry, am I making sense? So we have some A, B data, and someone starts entering A1, A2, A3. What's going to happen first is that this Moore machine, actually, I like initialized Moore machines, but okay, it's almost the same thing. This Moore will first output some kind of weird B that was in the internal state. And we haven't talked about initialized Moore machines, so maybe we should do that, but I don't know what to do now, because like we have this context switch of me talking, and I'm not doing a great job. Okay, so it's in some state.
So this is a register, right?
Yeah.
When you give it an A, it stores F of A in its state.
Yes, exactly.
Yes.
Now it stores in its internal state. It'll store F of A1. So this is out.
One-step memory.
Exactly. It's a one-step memory. So what you're talking about is if you have F, the identity function, this will be a one-step delay. But so it'll take it's in some state. I'm almost there. Sorry, everyone. So we start in some state B question mark or B0 or something, and then the first thing that happens is that we output B0. We update our state. State is B. To F of A1. Then we output F of A1 on the next thing.
The state is B, so no F yet. You're just storing the input directory. No. No, correct.
Does this look okay?
I think there are two ways to do it. Like use H in the output or use a.
I'm using F.
Now you
I'm
are
using F.
in the output.
No, I'm using, this is the identity.
Output is identity. Now I see. Yeah. Okay.
So this is the one that is supposed to be Fibonacci?
Say?
No, not yet, not yet.
No, not
A
yet.
composer
Okay.
will be Fibonacci.
Ah, okay.
This is just for any function I can turn it into a Moore machine
I see.
by caping as my state what the function does to the input. Okay. If you compose functions, it'll be composing these guys. I mean, the monoidal category, I think this is functorial in some nice way that we should say more precisely, but I don't know. Okay. Now, so for example, plus is a function from z times z to z. So I can record that as a little plus box. This will be a Moore machine. Its state will be an integer. It'll take in two integers as input and just add them in the next time step. But I can also take the identity box And as Jules mentioned, this is the delay, one step delay. So I take this identity box, I split like that, go like this, go like this, go like that, and that's Fibonacci. Oops. So what does it do? It starts, so you have to initialize these things, and Christina, that's also an algebra. So we talked about there's many algebras, but maybe they all look very similar. So for example, a map from 1,1 to SS is an initialization. It chooses some element of S. So if you had a map from SS to AB or something, and you had a map from 1,1 to SS, you'd have an initialized thing. And you could just continue these just as easily as you continue. This post-composition idea would have worked there too. Okay. Anyway, I don't know. Am I done or am I not done? Does anyone want to like see this? Do you understand what's happening? We initialize this wire as a 1. And what happens is that 1 is fed into here as an integer. And we initialize this wire as a 1, and that's fed into here as an integer. And then in the next time step, this thing updates, puts a 2 out here. But the thing that comes here is the previous 1, because this is a 1-step delay. So now a 1's coming in on this wire, a 2's coming in on this wire, and a 3 comes out, which is then exported. But a 2 is waiting here, and we get 5, et cetera.
I mean, in the end, you constructed a signal flow graph that does Fibonacci, no?
I guess so, yeah. Yeah.
What was the question?
Is this a signal flow? Is this just a signal?
I mean, this looks like the signal flow graphs that implement Fibonacci.
Signal flow because they're functions.
It's all Fibonacci.
Yeah.
But the graphical language is quite different.
But I mean, here there are implicitly the registers where there are explicit. But besides that, I mean, here the
Yeah.
function,
You're talking about like classical signal flow graphs, not like.
they're the same thing, the classical and the algebraic. I mean, they implement the same function. Just the only functions are black boxes where there are
This thing?
but for the rest it's really
Yeah. For any function, we get a Moore machine. And this is the identity.
A lot because of a parsing error. Okay.
Sorry. Okay. Any other questions? Okay.
So how much work would it be to unify this with the Petri nets?
A lot.
You think it's a lot of work?
Yes, because there is no way to put force on patterns.
So for every wiring diagram, there is an associated Petri net. But I don't know if that's what you want.
No, the real
For
problem.
workflow Petri nets, it's almost the same as the machines.
The real problem is that these machines here are defined in terms of stuff that comes in and stuff that comes out pretty naturally.
Yeah.
While a Petri net, as it is a closed system. So the problem is not wiring Petri nets together. The problem is giving a meaningful notion of what it means for a Petri net to have inputs and outputs. And that's a concept I've struggled with for 2 years. That's the main problem.
I'm surprised it's hard.
It is. Like from a process semantic point of view, it is hard. You know, you can say inputs and outputs are like message channels that synchronize transitions, or they are, like ways of sharing resources between places can be very different things.
What's the problem is that you have